Hey, welcome. So what we're going to be going over today is I'm going to share the notes. We are going to go over elastic force. Now, this will, I don't want to say it'll deviate from, whoops. Yeah. Um, it's not going to be different from the book, but the emphasis will be slightly different. The book goes into, it spends the bulk of this section on a couple of topics that I think are, eh, they're fine. They're fine to know, but to go into any of them in great depth would mostly just be equation pushing. So I'll introduce those, but mostly what I'm going to focus on is Hooke's law and the applications of that, and that is basically elastic force right there. So the topic is elastic force. And basically, the main rule we're going to use when looking at elastic forces is Hooke's law, like I was just saying. Now, what Hooke's law is saying, I'll give it to you in words, and then I'll give it the formulation, the mathematical formulation. It's basically saying it's a simplified model, but it's a model in which objects that are deformed from their natural shape experience a force to restore that shape. Sometimes it's called a restoring force. If we saw that term in previous chapters, but basically, that's what we mean. It's just a force that restores that shape, and that force is proportional to. All right, let me just say, yeah, I'll say proportional to the amount of deformation. Okay, so what does this mean? Well, the idea here and the way the book presents it is if you have delta L, this is your deformation. Then basically what this is saying is it's saying that your force is proportional to, and this symbol looks kind of like I don't know what it looks like. Looks like maybe an 8 without the tail. That is proportional to. Your force is proportional to delta L. Now, Hooke's law is more than just this proportionality rule, but that's the way of stating it in the way we have it here. It also depends on the material, and then on material, and that's where the constant of proportionality comes in. So we call that K. And basically what it's the book then writes it this way, F is equal to K delta L. And where this is often called either the spring constant or the stiffness constant. You'll hear me refer to it as the spring constant all the time because that's how I was taught, but really more specifically, it should be the stiffness constant. The idea is that deformation of an object, the higher the stiffness constant, the higher the force the object wants to return to its original shape with. Now, the thing is, this model, it's the limits of it are very, you can investigate them pretty clearly. Most materials have this to a certain extent, but then they reach this limit where their internal structure is deformed and they stop following this rule. So if you've ever seen one of those tension testers, that's basically it grabs two pieces of material and starts pulling it apart, and basically it's seeing where does the material start to deform, and that phenomenon you'll see is in materials, you get a little narrow band where the material starts to break apart is what's going on there. So that's what's going on there. Now, the way I was always shown this law, and I like this a little bit better, but mostly because it relates back to quantities we've already known. This is why I was taught it this way. It's that F is equal to negative K delta X. And in this case, it is really saying the same thing. but basically this is giving a little bit more information. One, it is indicating that the force is a vector, and so is and it's related to the displacement of the object. So the extent to which this thing has been displaced from its natural shape, that's the force. Now it's also negative. And the idea behind that, this negative basically means force acts in opposite direction of displacement. Now, the way you can think about this is that if you have a spring, and you stretch the spring, okay? So you have the string, you stretch it apart. The force is pulling in the opposite direction that you stretch it, okay? So if you're stretching it apart, the spring pulls it back together. If you have like a shock absorber spring and you're compressing it, the spring is pushing it apart. So it's acting in the opposite direction. Now, a lot of times when we deal with this, we only want magnitude, so that negative becomes kind of irrelevant. And particularly when you have a free body diagram and you show direction of forces with your, with the arrows, that negative becomes irrelevant. But if you're trying to express it exclusively mathematically, then this is how you do it. And you have to indicate that force does depend on displacement, and then from there, that the force is going to be going in the opposite direction of that. Now, the kinematics of this are interesting. So, for instance, you could predict that if you only had a spring force, you could set up Newton's laws and you would have an acceleration dependent on position, which is similar to what went on with drag. It's a little bit simpler to do, but we're still not going to go through the derivation of all the mechanics to do that correctly. Okay, so in any event, that is basically what we're going to be looking at there. Now, I will want to go through a few examples of this. But the main thing I want you to know for this class is this model applies fairly well to springs. Okay, so that is largely how we're going to use it, particularly when we get into the topic of energy. But we're basically going to be using Hooke's law. Now, it applies well to other things, just not for a particularly large displacement. So, for instance, something like steel, if you start compressing steel, it turns out you have a fairly, Hookean relationship to that, except you can't displace the steel very far before it just buckles and then the whole system is basically broken and the model no longer works. Okay, so that's kind of what's going on there. I will get to some examples with this, but before I do that, I want to just briefly talk about the other things that this chapter mentions. It talks about this idea of stress. And what a stress is, it's a force per unit area. Now, there is another per unit per unit area. There's another quantity that is more common in physics that also is a force per unit area, and that is pressure. Stress is force per unit area generally applied to solid objects. Pressure is force per unit area generally applied to fluids, and they behave differently under those conditions. Stress ends up being a vector quantity. I think stress is a vector quantity, but maybe not. I need to look more into that, so don't quote me on that. But pressure is not a vector quantity, so that's something to keep in mind. In any event, the idea is that when you have an extended three-dimensional object, it's not just relevant, where the force. It's not just relevant how much force is on that object. It's relevant how the force is distributed on that object. So, so that's the idea. Strain. Basically, what this is the. I don't know why I can't write words today. Strain. This is maybe those of you that have watched me take notes wonder if I can ever write words, but what strain is, it's basically the percent change in length of an object, generally due to a stress. Okay, so that's the idea. And the formula they give is delta L over L, and you can just see that's basically the change in the length divided by the original length. And a lot of times they'll put that as L naught, but that's how that works. Okay. Now then they talk about three different things. Young's modulus. And basically the way you can think, and then there's the shear modulus. And then there's the bulk modulus. Now you can go check these out in their different definitions in the book. But basically what these are descriptions of how, and they're not, and by description I really mean a mathematical description, like a quantification in a quantified description. These are descriptions of how materials respond to forces. Okay. You get into a class like statics, respond to forces. You get into a class like statics, these things start coming up a lot. Like I said, I don't really want to treat them here because the formulas, you can check out the formulas. Actually, I'll write them down. Why not? I've got them right here. So we have basically the delta L is equal to 1 over the Young's modulus, that's the Y, times the strain, which is F over A, or times the stress, that's the stress, times L naught. So you could basically, manipulate this stuff and figure out that basically what Young's modulus is, if you solved for Y, it's the stress divided by the strain. And that's perfectly fine. And generally what Young's modulus involves, this is materials under either compression or tension. Compression being, pushing something together, and tension being pulling something apart, compression or tension. So materials will have their own Young's modulus. Basically, what you do to determine the Young's modulus is you make a lot of stress and strain measurements, and then you take a ratio, and you can find the Young's modulus that way. It's a little more complicated than that, but that's the idea. Then the shear modulus it's very similar. It would end up being F over A times L naught over delta X. Now, the idea with that is a shear force is something that's kind of acting perpendicular to the long dimension of the object. So basically you can have this sideways deformation. That's why they give it delta X instead of an L, but it still end up being a kind of, it's a stress, against a kind of strain. But a lot of times this behavior of shear forces, particularly when the forces are imbalanced, it requires requires a different thing. And then the bulk modulus is basically, it's very similar to the Young's modulus, except it's for overall volumes, and it generally applies to when you have a uniform force around an entire solid object, or even possibly a fluid. But anyway, the bulk modulus, the B, ends up being F over A times V naught over V. And again, basically what that is, that ends up being the strain divided by the percent change in volume instead of the percent change in length. So all of these things end up being a little different. Again, I don't really think it's worth going into it too much, because again, it starts to be equation pushing at some point. Okay, so what I want to do is I want to talk just a couple of examples of that involve forces on springs. So example 1. You do something like this: a mass of 1.00 kilograms hangs on a Hookean spring. And this is a term you'll see. Basically, when you see Hookean spring, it means it obeys Hooke's law. On a Hookean spring with a spring constant or a stiffness constant. Again, you'll almost always hear me say spring constant, but that's just because I learned it. Stiffness constant is probably more accurate. With a spring constant of 1,250 newtons per meter. Now, I'm going to rewrite Hooke's law. So, and this is just the magnitudes without the vectors. It's K delta X. Now, we could put the negative there. I'll just put it out just to indicate opposite directions. Hopefully you can see that the units of K are newtons per meter. The units on the right should be newtons. The units of X would be meters, the SI units. So in order to get newtons on the right and the left, sorry, newtons was on the left. K would have to have units of newtons per meter. And basically that's what you can think about the spring constants. Like, okay, for this object, in order to extend it 1 meter, you would have to exert this many newtons. Now, again, oftentimes that's not possible. The newtons, the object will break before you ever get to that point. But the idea is that if it kept the same behavior and you were able to extend it or compress it 1 meter, then basically you would have this kind of you would have this kind of behavior. Okay, so that's kind of what's going on there. Now, when we talk about this, basically what we the question we might be asked is how much is the spring stretched? Okay. And in order to do this, and this is why I'm doing this, is basically we're going to go back to our Newton's, our free body diagram. And we think, okay, well, if we're hanging this thing from a spring, it's definitely got the force of gravity on it. But it's also this time, instead of having a normal force or a tension force, what it has, and I should say that's spring force right there, is a spring force in the upward direction. Okay. Now, if it's just hanging there, not moving, we can also say that the acceleration is 0. Now, if the acceleration is 0, then F net, we have our spring force in the upward direction, our gravitational force in the downward direction. Those are equal to 0. That's just going to say that our spring force is equal to our gravitational force. Well, how we're going to do that is we have K delta X. And this is, again, why sometimes this negative is not written. Because when you set it up with a free body diagram, you really only care about magnitudes. You know that the thing has been stretching down. If we left the negative there, we could do that. That would be fine. And we would get that is equal to mg. It's just giving you directional information that's important to know about. That's basically what's going on here. And then when we find this, we would get delta x equals mg over K and negative. And the negative is basically going to mean down. Now, again, that's why a lot of times it'll just get dropped because you know it's stretching down. Like you know which direction this thing is going. So you can drop the negative, you can leave the negative. Just realize that what it's telling you is a direction. Okay. And then you would have 1 kilogram times 10 divided by 1,250. And when you do that, you end up with 10 divided by 1250. And that's going to give you 0.008 meters, which would be 8 millimeters. Okay. Or 0.8 centimeters, however you prefer to express that. Okay, so that would be how you would look at that one. Now, next one I want to do, another type of problem we might see. A spring has a 0.500 kilogram mass suspended from it. And it stretches 25 centimeters. And I'll even go back and I'll even indicate this is Hookean. You then might be asked to find the spring constant. Okay. Now, the idea here is that the free body diagram is going to be essentially the same as we just looked at it. We're going to have our force of gravity, our spring, and it's hanging there just, just by itself. So it's got an extension of 25 centimeters, but it's not accelerating. So acceleration equals 0. Now, using the same analysis we just did, we can basically show that these two forces are equal. So we would say the spring force is equal to the force of gravity. And then I would just say, okay, the spring force is equal to K delta X, and that's equal to mg. Again, realizing that the negatives have canceled out, and we're already talking about a delta X of down. So that's the idea. But from there, you just get K is equal to mg over delta X. And that will be 0.5 times 10. And then important not to put 25 in here. I mean, you could, but in general, you should always put these things in SI. So the SI units would be meters. So 25 centimeters is 0.25 meters. So 0.25. And when you do that, you end up with 5 divided by 0.25. That is what is it? That's 5 times 4, which is 20. So that would be 20. And then in the numerator, you had newtons. In the denominator, you had meters. So again, it's newtons per meter. Okay. So that would be it for that one. All right. Now, one more thing I want to show you. It's something that looks like this. So I'm going to go put this in my notes over here. All right. And I'll that. And then also need okay. So we'll make these bigger. It's fine. So what we have here is we have this problem where a mass, whoops, that's what I wanted to do. A spring has 5 masses suspended from it at the following extension. So 50 grams, 2 centimeter extension, 100 grams, 5 centimeter extension, 250, 16, 531, 60, or 1061. And then the question was approximately, so the a question you might be asked is for approximately what extensions is the spring Hookean? Now, this is an interesting question, okay? Because the idea is that not all of these springs are going to be, they're not always going to be Hookean everywhere. Like a rubber band is a pretty decent example. When you put little tiny masses on rubber bands, they won't really start stretching. They really only start to behave Hookean once they get a little bit of stretch to them. And then actually, once they get a little bit more, they start, you start really extending the rubber. It stops being Hookean at that point. So a lot of times materials and things that stretch, they will behave Hookean, but only for certain extensions. Okay. And this is one of those things that I wanted to show. So what I'm actually going to do is I'm going to show how we could take a look at this. So I'm going to stop sharing this. I'm going to go over to the Desmos calculator. If you haven't seen the Desmos calculator, it's pretty cool. If you've never used it, it's a nice little cheap alternative to a graphing calculator. But basically what you can do is you can insert a table for Desmos, and then I'm going to call this the mass, and I'm going to call this the, I'll just call that X for the extension. And from there, what we have is we have 50 and 2. Okay, so what I want to do is I want to zoom out and notice it plotted it right here. So there's 50 and 2 right there. And then so 50 on the horizontal. So it's mass on the horizontal. So I'm actually going to change that. I think I want X and M. Oh, it's not liking that. Okay, so what if I do X0? Does it like that any better? Whatever. I guess we'll leave it. We'll leave it like that. And then so M and X. Okay, cool. So we've got extension here, basically a proxy for force up here. We could change this to force, but we know we just multiply, and we'd have to convert it to newtons, so to kilograms, and then into newtons. But this is basically a proxy for force. And then we have 105. Now, right now, looking at these, we can't really tell. Like, we could make a line between those two. And the idea is that basically, if this is Hookean, the relationship between these two will be linear. Okay. Every time we increase the force, basically when we're hanging the mass from it, that's a proxy for the spring force, because forces are balanced. The spring force is equivalent to the force of gravity. That's the idea. So we should see that as we increase the spring force, the deformation should stay the same. But the next one was it was 250 and 16. Okay, so zooming out a little bit more. Okay, I don't know, maybe. Hard to tell. And then we would have 531. And this is hard to tell because the scales are a little off, so we'll change this in just a bit. But last one was 1061. All right, so again, a little difficult to tell. So what I'm gonna do is I'm going to go to adjust this, and on my x-axis, I'm just gonna have that be from like 0 to 1000. Actually, I'll go to like 1200 just so all the points are there. And then the y-axis, I'm going to just have that go from 0 to 70. Okay. And there, now we've got something that's a little bit more reasonable. Okay. And this thing actually looks pretty Hookean. Like we can go in and change some things here, and we can do like a line between those 5 points, and it looks pretty straight. Now, generally we don't want to do that. We would want to do like a best fit line. So figuring out the best fit line is a little bit, I wonder, can I do a best fit line easily here? Figuring out the best fit line is a little bit tricky. But basically, I would say, looking at this relationship, I would say that you can draw a pretty reasonable approximation of this thing as a Hookean spring. Okay. So if I'm looking at it right now, I'd probably say, well, we can tell you what, we just do y equals 5x. Okay, so definitely not that. Y equals and y, the m is a proxy for the force. So oh no, x is on the y-axis. That's interesting. Okay. So we'll do 0.1. Okay. 0.15. Oh no, 0.08. Whoops, 0.08. A little bit less, 0.05. Okay, 0.06. 0.06 is getting pretty good. Okay, so we might say that slope of 0.06 is a pretty good fit for this thing. So we could say that this spring seems to be Hookean for all the measurements. Okay, because it does generally have a linear fit, meaning that, again, if there's a linear relationship between the amount of extension of the spring and the force applied to it. Okay, that's the basic idea. All right, so we could change that a little bit. That's a little 5, 9, 6, 1, 6, 2. Yeah, I don't know. Some of that looks pretty good. That looks probably about as good as we're gonna get to a best fit line, especially if we lock the y-intercept at 0. We could probably do better if we shifted it a little bit, but nevertheless, that's basically what we're getting here. Okay, so that's the general idea behind that one, and that's kind of how you can tell whether or not a spring is Hookean, is if you apply a force and you get linear extension, or extension that's proportional to the amount of force you apply. And you can kind of tell you get something pretty close to that, looking at the table as well. All right, so last thing I did want to talk about, so I need to stop my screen share. Maybe, if I can. No. Okay. Oh, it's down on my other screen. This is so weird. I never get how this works. Okay. All right. So I'll go back, share this. One of the things that's going to come up in the homework is that you're going to have not the homework that's due this coming week, but the homework that's due next week. Well, week after next, I guess. Is this idea of a spring on a ground. So the idea here is a lot of times these systems, someone will have the idea where you have a spring attached to something like a little cart here. And the idea is that, you can pull the cart away, or, it might not have wheels. If it has wheels, then the thing is definitely going to move. And, that's something we could look at, but we could do something like this where it's you basically have a spring acting horizontally now. Okay. So in this case, the idea here is that what you would get is you would get a free body diagram that looked kind of like this. So we'll talk about the FBD. Now, the first one, a lot of times you ignore friction. If it's rolling, like it has some friction, but for the most part, it's fairly small, at least particularly on the time scales we look at. So this one would have a force of gravity, because that cart has a weight. It would have a normal force. Those two would be equal, but it would also have a spring force to the left, or potentially, if that spring force also exerts a compression, you could also have a spring force to the right. I'll actually do that in dotted red line. So could be either direction. Okay. And if the spring is unstretched, you might not have any force. So the idea there is that the more you stretch this thing out, or the more you compress it, the more spring force you get. In this one, what you might have, let's say you stretched it for this other one. You stretched it, so you still have FG and normal, and those don't really change. Those are not particularly relevant for this one. But let's say you stretched to the right, and so your spring force is back to the left. What you might then have is a friction force to the right. And, depending on whether or not this thing was accelerating, that friction force could be, greater than, less than, or equal to the spring force. Okay. So that's something just worth considering there, when you have something like this. Okay, so just so you're familiar with that, be on the lookout for those. Know that this is the basic free body diagram setup you're going to want, and then know how to apply Newton's second law to this system, or Newton's first law, depending on what it is. So I'm going to go ahead and end this lecture there. Thank you for joining me. I will see you next time.